My friend, you are entering a world of Pico-8. My name's Dave. We're at pico-8-edu.com. Let's start it up. Today our goal is to make Flappy Bird. Along the way we're going to talk about state, acceleration, collision, and a little something called lerp. The first thing I want to talk about is state. State is just the concept of what is a thing doing. It can be really broad. It can be like, what is the whole game doing? What sort of mode are we in? Or it can be really specific, like, is our character running and jumping, or is our character swimming? Because like the code for swimming, the physics are going to be different. The controls are going to be a little bit different versus running around and jumping. So different code's going to be running, and you're going to want to have something that keeps track of what are we doing right now. And I think a really good use for state is organizing our project into what is commonly called scenes. So a game will normally start on like a title screen, and it'll show you the name of the game, and then you press a button and the state of the whole game changes, and you're in like a gameplay state. So I'm going to open up a new tab here. I'm going to make this the title scene. This will sort of mirror our main functions. I'll make a global variable called scene, and it'll be a string that just holds title. And in the draw, now, usually we just do CLS like this. We can actually pass a color in here. I'm going to use 12. And we'll just print the word bird. Right now, we'll just do it at 0, 0 with a color of 7. Keep it simple. Now I'm going to make a new one. And we'll keep our game code in here. Now in game init, we'll say scene equals and a string game. Just so we can tell the difference, we'll make the background of this 15. And that's it. Back in our title scene, we want to check if the player presses any button, we change state to the game scene. So I'm going to do if button P, and I'm not going to pass anything in. And I'm going to do is greater than 0, then. And this is a little bit of a hack, but it's kind of cool. If you don't pass anything into button P, it brings back a code that sort of contains all the buttons that are pressed. And if no buttons are pressed, that code winds up being 0. And so if I just check if it's any number above 0, then it's like I'm asking, are any buttons being pressed? So I'll just say game init. So we got to go back to our main here. In our init, we're just going to run title init. And then down here, this is where we're going to decide which update and draw we use. Now there's a concept in game programming called a state machine. It's how you write the code that decides what code to run depending on what state you're in. And there's tons of ways to do it. And I've spent a good amount of time trying to write the ultimate state machine that just does everything, that I can reuse everywhere, that is robust, that solves all my problems. And kind of where I'm at now, I think the best way to do it is to do it as simply as possible. Get away with writing as little as you can. So I'm going to show you the bare bones version because I think it's the best way to start learning. And I also think that it's fine. I think it's appropriate in a lot of situations. So we can just write if scene is equal to title, then else if scene is equal to game, then end. So if the scene is title, then title update. If the scene is game, then game update. And we can basically just copy and paste. Change these to draw. Boom. So, title screen, press a button, game scene. Now, I'll definitely show you more robust ways of doing this later. For this is all we need. And you'll kind of get used to this idea of switching modes. So just to run through what's happening, when our game starts, our regular init function, all it does is it calls title init. All title init is doing is saying, hey, the scene is title. On our update, checks, is the scene title? Well, yeah. So it jumps over, we run our title update, checks for that button press. During the draw, the scene is title, does our title draw, right? In the update, if we press that button, it runs game init. Game init just switches the scene to game. And all that does is, when it gets to this logic, it says, if scene is equal to title, well, no. Then, else if scene is equal to game, yeah. Run game update, run game draw. And now we don't actually have to write anything else in this. So I'm just going to say these are our Pico functions, and we really won't touch them anymore. I should change this. This should be the title of the game. And then for this tab, this will be our bird. We've done this kind of thing before. Bird new. Return a table. Give it an X of 16, a Y of 32. Give it a radius of 3. Leave little notes to ourselves. Now I'm gonna do dx equals 0 and dy equals 0. And this will be our velocity. And so all that is, I think we've done this before, it's just like the distance that our bird will be moving every frame. We'll write function bird update, pass in b for bird, and we'll do function bird draw, and also pass in our bird. And right now, I just want to draw a circle for our bird. So we'll draw a circle at the b.x, b.y, with a b.r radius and color 3. And then in our game scene, we will just do bird equals bird new, bird update bird, bird draw bird. We can run that. Got our title, got our game scene, draws our little bird. Now we want to move our bird with gravity. And gravity is a downward force, and it will accelerate the bird downward. So our gravity, it's not really going to change. It doesn't ever need to be reset. And so I'm going to make it a global variable just up here, tab 0, up at the top, grav equals, and I'm going to do 1/8. I'm going to be using a lot of numbers that are fractions like this, and I'm not going to explain it in this video, but down the road, I'm working on something for a later video. Okay, I want to show you this in sort of 2 ways, just so you really understand the concept of acceleration. If I do b.dy, like our y velocity, equals grav, and then at the end we update our b.x by adding b.dx and b.y plus equals b.dy. We get this constant motion. So that's like speed, but we want acceleration. We want that motion to keep getting faster. So what we really want is b.dy plus equals grav. And every frame, our velocity on that axis is going to be more and more and more. And I can just kind of illustrate this. If I give us a constant x speed, and I just comment this out real quick, and maybe I just change the radius to, what happens if it's 0? Oh yeah, there you go. Even if I set this to 0, yeah, there you go. So you can really see the change in distance every frame gets greater and greater because that velocity is accelerating. What we can do we want to be able to flap, right? We want these sort of bounces in the air. And so we can define our flap strength. And we can do if button P is greater than 0, so like any button, then b.dy is equal to b.flap. There you go. And let's bring our CLS back. Let's remove this. Let's get our radius back. Yeah. So now we've got that sort of flapping motion. And the reason we want to say b.dy equals b-flap instead of plus equals b-flap. If you have a certain amount of force down, and then you're just like counteracting that force, you can like kind of hover, and that's not really what we want. We want those arcs like always. And we don't want to like, we don't want it to stack into this like, that's not the game we want to make. So when you hit that button, it sets that initial velocity upward to our flap power, and gravity will pull us down. Okay, we're gonna need some pipes. I am going to go up here, define a bunch of settings that are just gonna apply to like all pipes and creating pipes. They're all gonna have the same speed. They're all gonna have the same width. There's gonna be a gap in between the pipes. And I want that to be random, but I want there to be like a minimum and a maximum. I'm gonna define gap min equals 40. And it'll just make it easier to write if instead of like a maximum, I do like a range. So like the range above the minimum. So RNG for range in this case. And then like that gap is going to have a Y value. So we'll have a Y min, like the top. We want it like 12 from the top. I think the range should be like 128 minus Y min minus gap min, maybe? Here, let me draw this out. Got our screen. We've got our like, that's the minimum we want to start at. And then if this is like a minimum of 40, and we kind of want our maximum to be here, we kind of want to minus that 40. So like here-ish. So we want this to be, yeah, we'll see if that works. And then I kind of want our pipes to have like a little wiggle room as far as their like X position from each other, like the distance between them. So I'll just do X min equals 80 and X range equals 50. Let's make a pipes tab. We just kind of want to make all our pipes in one go. Make an empty table for I equals 1, 3. I don't think we'll ever have 3 on screen at a time, but why not? And we'll say, we'll make a table at that I position in our pipes table. And we'll just set the X to 0, the Y to 0, and the gap to 0 for now. And return the table. Because usually what we've done when we've had like a table of tables like this, where things are like going across the screen or whatever, or like the bullets, we've had like pretty simple logic if we're reusing the same table and just resetting its position over and over again. Or we've been like deleting it from the table and creating new ones. And it's kind of bad practice to be pulling things out of a table all the time and like creating new things. The memory in the computer, like it's constantly sort of reshuffling the table and trying to keep it all compact and stuff. And if we just sort of like manage reusing stuff, we can give the computer a break. There's something called the garbage collector, which is like a program that runs in the background. And when we are deleting tables, it's the one picking them up and like figuring out which ones aren't being used anymore. And we can give the garbage collector a break if we're being more responsible about recycling our tables. So what we can do right here is we can do pipe init, pass in this table we just made, and our like master table of pipes. So I'm writing this function pipe init that takes in a specific pipe and the full table of pipes. And we're going to use this at the beginning to initialize our 3 pipes. And then we're also going to use it when one pipe reaches the end of the screen. We're just going to pass that pipe in and it's going to move it over. We're going to want an X, a Y, and a gap. And we can do random X range plus X min, random Y range plus Y min, and random gap range plus gap min. And then I just want to like make sure if we chose like a Y that's here and our gap is like too big, I just want to scooch it back up to this minimum. So Y equals min Y, Y min plus Y range minus gap. So we're saying take whatever's smallest. If you're like way up here, doesn't matter, you're fine. If not, we want to find the lowest place we want to be minus the gap we chose. Now we want to go through our pipe table, our table of pipes. We want to find the rightmost pipe. So whatever is furthest to the right, we want to move to the right of that. Because later on, we won't know what order things are in. And this really only matters if there's more than one thing in the table. So like when we do this, the very first pipe, it won't matter. But then every time after that, it will. So we'll say if the length of table is greater than 0, using our octothorpe. X max equals 0. And we'll just say for O, O standing for other pipe, in all table, do X max equals max, X max, or O dot X. X plus equals X max. What this is doing, if there's more than one pipe in the table, we make a local temporary variable, X max, set it to 0. We loop through all of them, and we set that X max to whatever's greater itself, or if there's something with a greater X more to the right, that's our new X max. And then this X that we set up here, our random, we add the rightmost pipe's X to that. We get our random spacing added to that maximum X value. Then we can just do p.x equals x, p.y equals y, p.gap equals gap. All right, and we don't want to have to call this function on every single pipe. We're just gonna give it all the pipes. p.x plus equals our pipe speed. And if p.x is less than negative p width, so if it's like totally off the screen, then pipe init p table. So all this does is takes this pipe, redoes this, moves it past our rightmost pipe. Do a similar thing for drawing. For P in all table, do. Now we're gonna want to draw two different rectangles, one for the top, one for the bottom. Right now, because I want to show you something, I am just going to draw the gap. So we're going to have our top pipe and our bottom pipe, and right now we're just drawing the gap. So we've got our P, X, and Y, start there. And then the second coordinate is PX plus the width and PY plus the gap. And this is what we're trying to draw in here. Let's go back to our game scene. We're going to want to do pipes equals pipes new, pipes update pipes. And I actually want to draw the pipes under the bird. Little bug here. If p.x is less than or equal to negative p width, because we want it off the screen. Okay. Okay, since we're accounting for the gap over here, I think here we don't need to do minus the gap. We need to account for the amount we want as a buffer on the top and the bottom. So I'm just doing y min times 2, and that seems to give me the output I want. Hey, Future Dave here. There's a problem with this code. I made a small test project to show you why. So if we generate 64 pipes using this function, you can start to see the problem. When we try to randomize the Y position and the gap size at the same time and then we shift the Y position up to accommodate, it means a lot of our pipes will favor sitting at the bottom of the screen. We can fix this by choosing the random value for the Y after the gap size is decided, and then subtracting that specific gap from the Y range. That way we get a nice even distribution. So you can fix this in your version and it'll be better than mine. Okay, let's talk about collision. I'm gonna put, if we were doing a lot with collision, I might make its own tab. Right now, I think I'm just gonna have the game scene handle collision. So I'm just gonna put it down at the bottom here. We'll just do function collide. We'll take in the bird and we'll take in the table of pipes. Now there are several different kinds of collision. The only one we're going to use here is called axis aligned bounding box collision. And all that means is if you have two rectangles and their rotation is the same, they are aligned, there's just a couple checks to do to figure out if they are colliding. And the strategy is basically to eliminate possibilities as quickly and efficiently as possible. So the pipes, for most of their life, are going to be to the right of the bird. Let's say this is the hitbox of the bird. If the right side of the bird is less than the left side of the pipe, that is a good check. For P and all table, do if bird dot x plus bird dot radius is greater than pipe dot x. So if this is false, we want to get out. And if it's true, then we want to return true. This will loop through every pipe and check this. And if any of them are true, then the function returns here and this doesn't run and it won't check any more pipes. Because we only really need to hit one. Now, what if this pipe is behind the bird? Like we've passed it. This right side is still past this left side. Our next check should probably be if this left side of the bird is less than the right side of this pipe. So we'll do and b dot x minus b dot r, because the position of the bird is the middle of the bird. The right side is plus r, the left side is minus r. Is less than p dot x plus p width, because this is the x and you want the right side, get that plus width. That means our bird has to be somewhere in here if both of those are true. Now, right now, I want to show you like the classical collision where we're seeing if it's inside this box. We're going to kind of flip it in a minute because this is like the gap we want to fly through. But just hang with me here. We're basically going to do the same thing this way. So, bottom of the bird, b dot y plus b dot r. Top of this rectangle, p dot y. And top of the bird, b dot y minus b dot r, is less than bottom of this rectangle, p dot y plus p dot gap. If all of those are true, definitely somewhere in here, definitely colliding. Return true. Now we're doing 1, 2, 3, 4 checks in this if. But the nice thing about and is that if any of these are false, it doesn't check anything after it. It just skips and does the next pipe in the for loop, or just ends the for loop and returns false. So the way you can kind of structure this, the reason this is a good way to do it is most of the time when those pipes are to the right of the bird, this very first check is going to rule them out and it's going to move on. Okay, we can do in our game update, we can do if collide, pass in the bird, pass in all the pipes, then we'll just call a function bird lose. And let's go make that. Let's put this right above update bird. And here's what I'll do. In the bird new, we'll have an alive variable. In our losing function, we'll just do bird.alive equals false. And we'll make it like bounce backwards. So we'll do b.dy equals -3, b.dx equals -1/4. And then in the update, we'll just do a check and b.alive so that you can only flap if you're alive. And we can do at the beginning here, we'll just do if the bird like falls completely off the screen, we'll go back to the title. And I'll just do like an arbitrary number here. And I'll return early here if we're like totally off the screen and hit the title. Don't even run the rest of this. All right. So we've got this game where we're trying to avoid these gaps. And if we like land on top, oh, we can bounce off multiples. So we should probably, as soon as the bird hits one, we'll just wrap the pipes update. So they'll only move and update if the bird is alive. Nice. Let's see if I can hit the bottom of one of these. Yeah. So this is like the opposite of what we want. So let's change our collision. These first two checks are good. We want to check if the top of the bird is above this or the bottom of the bird is below this. So I'm going to wrap this in parentheses and change this to or. And we want by minus br for the top is less than the top of the gap, or by plus br is greater than py plus the gap. And now we should be safe as long as we're flying through these gaps. And if we aren't, then we get knocked. Okay, let's draw the pipes correctly. Get rid of this. We want to draw the top. We'll keep it simple. P.x 0, P.x plus P width, P.y 3, P.x, P.y plus P.gap, P.x plus P width, our constant, all the way down to the bottom of the screen, 128. color of 3. Cool, we got pipes. I think we're kind of getting like stuck. The bird can like keep bouncing off the pipes. Yeah, we don't really want that. So in our collide, we're just gonna write if not b.alive, return. So all this does, if our bird isn't alive, return early. Don't even bother checking. Now just a little game design thing. I'm gonna shrink our radius a little bit. And down where we're drawing our bird, I'm gonna just make it draw a little bigger than what it's checking. And I think this is a good like little game design thing. You kind of want to be a little kind to your player. Let them feel like they just squeaked by, even if they probably should have hit it. If they feel like they just barely dodged it, it feels nice. Okay, we probably want to score. So up here when the game starts, I'm going to set a high score, call it best, set that to 0. When the game starts in our game init, I'm going to make a variable called score, set that to 0. That's the score for our current game. You might want to do like right when the bird passes a pipe, their score goes up. We're so close to the left side of the screen. I think I'm just going to do whenever a pipe goes off the left side and gets reset, that's when the score goes up. So just here in pipes update, score plus equals 1. And then right here, when the bird loses, we want to update our high score, and we'll just say best equals max score, comma best. So whatever's highest, the current score or the previous best, that's what the best is now. You could make a new tab for UI. I'm going to put it right here. We're going to draw at the top left of the screen the word score, so a string, and then we want the number. I showed you before, you can't just add a string and a number together. Because what do you get? Do you get a number? You can do something called concatenation to sort of glue strings together. And the way you do it is ... So what this will do, it'll take the string score, it'll turn our score number into a string, and it will glue them together into one string. Print that in the upper left-hand corner. And we'll just do if best is greater than 0. So if we've set a high score, we want to show that as well. Print best ... best, comma, to 8, 1. Let me just make it a slightly different color. In our game scene, game draw, at the end we want to do score draw. And then on the title screen, I just want to do if best is greater than 0, then score draw. So we don't want to show the score like the first time the player opens it, but then every time after that, we want them to be able to see. So yeah, we've got our best score updates, and let's see if we can beat it. Yep, and then our best score updates. I'm just going to position our title, center it, set the Y to like 60. What I can do is local text equals bird. And then to center this, we can do 64 minus the length of our string text. So it's the same octothorpe hashtag symbol that we get the length of tables with. We can use to get the length of a string. And because the Pico-8 font, every letter is 4 pixels, including the space between letters, we can do half of that. So the length times 2 pixels, the center of the screen, we basically want half the width of that text. And hey, there it's centered. And we can change the title and it's always centered. I want to give our bird a little more character. I'm going to make an angle variable. I'm also going to define some colors. C bod equals 3. C nose equals 9. C wing equals 1. In our bird draw, do b.a for angle equals b.dy divided by 16. We want the bird to change its angle depending on whether it's moving up or down. We'll draw its nose first. We're just going to use basically circles for this. b.x plus cosine of, you know what, let me make a local a equals b.a, just so I'm not typing b.a like everywhere. Cosine a times b.r plus 2 b.y minus sine of a times b.r plus 2. And we'll make this the same size as the radius. We're using our trig functions to find the point on the circle around the center of the bird to the right, offset by 2. We'll draw a tail. b.x plus cosine a minus 0.5, right? Because we want to get the opposite of the angle in turns. So half of a turn times b.r, b.y minus sine a minus 0.5 times b.r, b.r plus 1, b.color of the body. I think I want the body to be a little bigger. Change this to b.c bod. And then I want to give it a big eye. Let me see what that looks like. All right. That's pretty good. I think that tail could be bigger. Just make some adjustments to make this cute. Now it's a very sudden motion when you flap, because it like instantly flips up. So I want to introduce you to, I'll just put this in our main tab, linear interpolation, also known as lerp. It's going to take 3 values, a, b, and t. Here's the formula. Return parentheses 1 minus t times a plus t times b. What this is going to do, if you have two values, in this case we're going to use it for the angle. You could use it for position. And you want to get a value between those two. You define this as A, this as B, and then T is like a percentage. So 0.5 is going to be here, 0.25 is there, 0.75 is there. And you can use this. We can go to our bird draw. We can say local PA for previous angle equals B.A. We can change B.A to what we want it to be. And then we can do A equals lerp, previous angle, the target angle, and then just take us halfway there. And this will wind up smoothing things out visually. So now it's like, it's still snappy, but it's a little smoother. Now a bird needs wings. Let's make wings. After the body, do wings. We kind of want the wing like set back, and then we want to move it up and down depending on if we're going up or down. Local wing Y, and then we'll do like wing O for offset. Bird.y plus bird.r. 2 plus 1. And 4 for the offset. We'll do if b.dy is greater than 0. So if the bird is falling down, then wing y is equal to b.y minus b.r minus 1. And wing offset is equal to -2. Up here, I want a wing position. Set that to the same as the y. This is the wing's y position. b.wing equals lerp b.wing wy 0.5. Smooth out its motion. Then we will do oval fill b.x minus 7, b.wing minus 2, b.x, b.wing plus 2, b.c wing, and oval fill. The wing's going to be like 2 ovals. b.x minus 7, b.wing minus 3, b.x minus 2, b.wing plus wing offset, b.c wing. All right. Got a nice little flapping animation. And we can actually like change this to 0.4, and it'll kind of make it lag behind a little bit and give us some like fun secondary motion. And I want to do one more thing. Up here at the top of our bird draw, I want the rotation to act like this when it's alive. Else, I want b.a minus equals 1 over 32. I just want it to kind of like spin. And now the wing looks weird like that. So let's adjust this. Let's do if b dot alive then, and we will take all of this, indent it, else we'll just do circ fill b dot x plus cosine a minus 0.5 times b dot r plus 1 plus 3. B dot y minus sine a minus 0.5 times b dot r plus 1 b dot r b dot c wing for the color. Let's see if that's good. Yeah, so that kind of like convincingly makes it look like the bird's wing is rotating with the bird. To celebrate learning about lerp a little bit, calling this Lerpy Bird. Now we've made some like pretty substantial games at this point. You probably want to start saving your work, which I haven't shown you how to do. So even in the web version, you can save your game and load games. There's a few different formats. The main format is a P8 file, which is basically just like a text file full of the data. It includes like all the sprite data and everything. And you can just do save lerpybird.p8. You don't even need the P8, and it'll save that, and it'll save it to your downloads. You can also, Pico-8 has kind of a weird format where it saves it as a PNG. It's an image, and secretly encoded in the image is all the game data. And if you want to do that, your first two lines up here should be a comment, should be the title and just a little like credit to yourself. Run the game when you think it looks good, which is, it's a little hard to like capture. You want to hit Control-7 and it'll say capture label image. And then you can do save lerpybird.png, and it will save that image cart with a cover of that screenshot you took and the title and the name. You can also do save at clip and press Control-C, and it gives you like a bunch of data. This is really long. I'm going to delete this because we don't want our cart in our cart. But this is like compressed data that contains everything we just did. And one more cool one, I don't know where this is documented, but it's neat. You can do save at URL. Oh, it's too long. We made our program too long. All right, well, good example. If your program is short enough, it will actually encode the whole program as part of this address, and you can copy the whole address and just send it to anybody, and it'll instantly load up what you've written in their browser. It's a cool way to share like little snippets. But unfortunately, our Flappy Bird is just a little too long. So yeah, you can save P8 files and .png files, and then just like drag them onto the browser, and it'll load it up, and so you can continue your work. Just remember to save, you know, since it's on the web, it's using a temporary disk. It gives that warning at the beginning that you're on a temporary disk, so when you close the browser, it clears it. A nice reason to buy Pico-8 is that like it saves backups while you work. It just uses your computer's disk. You can just hit Control-S and it saves it to your disk. It's really, Really handy. You can also do export, and you can export like a standalone .exe file for Windows, .app for Mac. There's like a Linux and Raspberry Pi version it exports. There's a web export. It's really nice. So if you really like wanna get into it, I think it's worth the like $15 it costs. So that's our Flappy Bird. We learned about managing state. We have that title screen. We've got the acceleration with the gravity. We've got collision when you hit things. We worked in a little bit of the lerp to help smooth out our animation. I think now you could do a lot with this using the knowledge you have. I think you could like make clouds in the background out of like circles. Just do it like the same way as the star field we did before, a table of tables, just drawing circles in the background, white circles. You could do like mountains if you want to use the sprite sheet and draw like little triangles or something, have them go by. You can fiddle with the code for the speed. You could change gravity. You could, I don't know, you could use the collision code. You could make coins that you have to collect or something. I don't know. Like, be creative, have fun with it. There's a lot you could build on from here. You could also improve these pipes. You could make them into something else entirely. You could change the color of the bird. Express yourself. But that's all the time I've got today. So I gotta get going. I'll catch you in the next one.